Today we're going to be talking about section 1.2, reduced row echelon form. What is reduced row echelon form? It's a form of matrix that has the following four properties. So let's go over what each of these properties mean. So if we have a matrix, our first property says that the leading entry in each non-zero row is a 1. So the leading entry is just going to be the leftmost non-zero entry. So for instance, if we had a row that had a bunch of zeros and then had a non-zero entry, that entry needs to be a 1. Every leading one is the only non-zero entry in its column. What that means is if we have our leading ones, then everything else in that column has to be zeros. The leading entry of a row is in a column to the right of the leading entry of the row above it. What that means is we're making sort of a quasi-diagonal. So if I have a 1 in this first column, that would be a leading entry. It would have to be above this 1 that I have in the third column. And let's go ahead and fill that column out with the zeros. And if I have any rows of all zeros, those would need to be on the bottom. So for instance, let's say I had a row of all zeros, that would have to be my bottom row. I couldn't have it be above these rows with the 1s. And it looks like we're missing one more leading entry. Let's say it's here. So if that's our leading 1, then this would have to be a 0. Any of the other things that we have, oops, sorry, and this column has all these zeros too. Any of these other empty spots that we have aren't dictated by reduced row echelon form. So they can kind of be anything that you want. So for instance, this could be a 3. It wouldn't have to be a 0 because there is no leading 1 in this column. Similarly, there's no leading 1 in this last column because our last row is all zeros. So this could be anything you might want to have. So again, the boxed places are our leading entries, our leading ones. These locations are sometimes called pivot positions. So if you hear me talking about pivot positions, that's what I mean, just these spots that are leading entries. And there you go. Sometimes, or more often, we'll see this in square matrices. So if you have a square matrix with no rows of all zeros, what this will look like is just 1s on the diagonal and zeros everywhere else. This is sometimes called an identity matrix. We talked about augmented matrices in class on Monday. So that might look like our row echelon form has the form of the identity matrix on the left-hand side, and then whatever numbers we might have on the right-hand side. So this would look like our augmented matrix. Now, why would we want reduced row echelon form? Well, we talked on Monday about the fact that we can view every single one of these rows as an equation. So for instance, this could be our first equation, our second equation, and our third equation. And each of our columns might represent a variable. So if we were to read off these 3 equations off of the matrix, what we have is 1 copy of x1 plus no copies of x2 plus no copies of x3 equals 3. The second equation reads no copies of x1 plus 1 copy of x2 plus no copies of x3 equals 2. And equation 3 reads no copies of x1, no copies of x2, and 1 copy of x3 equals 7. So this is really useful because basically what we're doing is we're able to just read off the answers in this rightmost column of our augmented matrix. We're able to read off the answers for the variables. So if possible, we want to get our matrix into reduced row echelon form so that we can easily read off the solution to our system of linear equations. So just as a reminder from Monday's class, how might we actually get a matrix into reduced row echelon form? Well, we have 3 elementary row operations. Our 3 elementary row operations are replacement, so we can replace one row by the sum of itself and a multiple of another row. Interchange, which is just swapping 2 rows, and scaling, which is multiplying all entries in a row by a non-zero constant. These are fairly self-explanatory. The one thing that I want to make sure we're clear on is the fact that if you do one of these operations, you have to do it to the whole entire row. So for instance, if you added row 1 to row 2, you would have to add every single element in row 1 to every single element in row 2. So here are our row operations, and we know what we're aiming for. We're aiming for getting into reduced row echelon form. How do we go about doing it? Well, if you do enough row operations, you'll likely eventually get there. But there is an algorithm that might help us get there a little bit faster. So what is that algorithm? Here it is. So the first thing that we want to do as we're trying to get our matrix into reduced row echelon form is we want to find a row with an entry in the first columns and move that row to the top. So if we are looking at our matrix, we basically want to identify something with its leading entry in the first column and make sure we move it to the top. And ultimately, we want that to be a 1. So our second step is to scale that top row so the leading term is a 1. Then we want to use row replacement to get zeros underneath of that 1. So that'll look like once we have the 1, using row replacement to get zeros all the way down. And then we repeat this for the second column. So we'll find something with a leading term in the second column. We'll scale it to get that to be a 1, and then we'll use row replacement to get zeros all the way down that column. And we keep on going until we have sort of 1s down the diagonal. Once we do that, we'll start with the bottom row and try to get zeros up. So as we reach step 4, what our matrix will end up looking like is 1s on the diagonal, zeros underneath, and something random going on up here. So at step 4, we've got 1s on the diagonal, zeros underneath, and stuff happening up in the upper right-hand part. So step 5 says we'll start with the bottom row and we'll use row replacement to get zeros above that leading 1. So we work our way up to get zeros up here. Then what do? We start repeating going up the rows this time. So we look at this 1 right above it. We use that 1 to get zeros going up, and so on. So this is our basic technique. And we do this until we get into reduced row echelon form. This is a little bit messy, and I think it's a lot easier to see how to do this with an actual example. So let's give it a try. So let's maybe do an example where we've got x2 equals 7. This is our system of linear equations. 2x1 plus 6x2 plus 4x3 equals to 2, and minus x1 plus 2x3 equals to 4. So our first step, of course, is to get this into augmented matrix. So our first equation reads no x1s plus 1x2 plus no x3s equals 7. Our second equation is 2, 6, 4, 2, and our third equation is minus 1, 0, 2, 4. So our first step of our process is to find a row where the leading term is non-zero. So we have 2 choices here. We can either take the second row or the third row. Let's take the second row. We want to move that to the top. So we'll switch rows 1 and 2 so that what was the second row will be our first row instead. So we've got 2, 6, 4, 2 is now the first row, 0, 1, 0, 7 is now the second row, and our third row remains untouched. The next step in our process is instead of a 2 here, we want to turn that into a 1. So we can do that by scaling. So we'll take row 1 and we'll just replace it by half of row 1. So we divide that entire row by 2. Again, the main point here is we need to divide every single entry in that row by 2. So the 2 becomes a 1, the 6 becomes a 3, the 4 becomes a 2, and the 2 becomes a 1, and the other 2 rows remain the same because we haven't done anything with them yet. All right, our next step is to try to get zeros everywhere underneath of that leading 1. We've already got a 0 in the second row, so we focus on the third row. If we simply add the first row and the third row together. That would give us a 0 right here where we want it. So let's go ahead and do that. So we take row 3 and we replace it by row 3 plus row 1. So this is row replacement, that operation. So our first and second row remain the same because right now we're just focusing on row 3. And remember, we have to add every single entry. So our first entry is 1 plus -1, which is 0. Our second entry was a 0, but now we have to add the entry of the first row to it. So this becomes a 3. We have 2 in the first row and 2 in the third row. So adding those together gives us a 4. And similarly, 1 and 4 makes 5 for the last entry in the third row. So this is our new third row. Okay, we have achieved our first goal of getting a 1 in the starting spot and zeros underneath of it. So now we want to find an entry for the second column. It turns out we already have it, and it's already a 1, so we're done with those steps. Now we want to get a 0 underneath of it. So how would we do that? Well, if we subtract 3 copies of the second row from the third row, then we would 0 out that term. So we're going to go ahead and take row 3 and we're going to replace it by row 3 minus 3 copies of row 2. So the first 2 rows remain the same because again, we're only trying to mess with the third row. The third row, 3 copies of the 0 here is still 0, and added to 0 is still 0. So that's good. And that's the reason, incidentally, why we start off with getting zeros in that column so that we don't screw up that column when we do further operations later down the line. Now, minus 3 copies of 1 is -3, plus 3 is 0. Excellent, that's what we were trying to accomplish. Minus 3 copies of 0 is 0, and plus 4 is still 4. Minus 3 copies of 7 is -21, plus 5 is -16. All right, so we now have our first column and our second column taken care of. And so now we just want to get a 1 in the third column, and we can do that by dividing that third row or scaling that third row by 1/4. So again, our first 2 rows remain the same. 0, 1, 0, 7, and our last row becomes 1, -4. Okay, so we have now achieved up through step 4 in our process. What do we do from here? Well, now we want to, starting from the bottom, get zeros working our way up. So our first issue is this 2 here in the first row. We want to get rid of that. So how do we get rid of that? Well, we can subtract 2 copies of the third row from the first row. So we'll replace row 1 with row 1 minus 2 copies of row 3. So 2 times 0 will leave the 1 alone. 2 times 0 will leave the 3 alone. This is why we did our first steps first. And then -2 times 1 is -2, plus 2 is 0. And again, we have to do that with our last column as well. So -2 times -4 is 8, plus 1 is 9. And our second row and our third row remain the same. Okay. Now our third column is good. It's got the 1 and 0s everywhere else. So our only last remaining problem is this 3. So we can get rid of this by row replacement. So if we take row 1, we can replace it by row 1 minus 3 copies of row 2 to get rid of that 3. And luckily, everywhere else in row 2 is 0. So we just have to worry about the 1 here and the 7 here. That will actually change row 1. So the first entry in row 1 remains the same. -3 times 1 is -3, plus 3 is 0. Excellent, that's what we were hoping for. The 0 stays the same, and then -3 times 7 is -21. -21 plus 9 is negative 12. All right, we have successfully gotten this into reduced row echelon form. So our left-hand side is reduced row echelon form, and we can just read our answers off of the right-hand side. So our answer to this is x1 equals negative 12, x2 equals 7, and x3 equals negative 4. We can double check that those answers work by actually plugging them in to our 3 original equations up here. And you'll see that if you do that, all of these end up working out. So that is how you get a matrix into reduced row echelon form. We'll do a lot more practice on Thursday. See you then.